Hi, guys. Let me just let everybody else in the meeting here. How you guys doing this morning? Good. All right, so just some administrative stuff while we're waiting for others to arrive. So let's not forget that tomorrow we have homework due. So the homework due tomorrow it's listed on our page, but give me a sec. 2.5, 2.6, and 4.1 is the homework that's due. We're going to wrap up 4.1 this morning. And then we'll start 4.2, and then at the end of class I can answer any questions about 4.1 or other topics that you guys might have. Also, don't forget tomorrow, I'm trying to let people into the meeting as we go. Tomorrow we have a quiz, and it's going to be like last time, but the quiz is going to open up. Quiz is going to open up at 3 o'clock tomorrow, just like last week. Okay, so the quiz will open up at 3 o'clock tomorrow, and it will be open for 24 hours, so until 3 o'clock on Friday. So make sure that you start it no later than 2 o'clock on Friday, so you have plenty of time to take it, upload it, download it, whatever you need to do. Okay, and the quiz, like we said on the Canvas page, the quiz is on 2.5, 2.6, and part of 4.1, like the parts that we've covered on Monday. Okay, so let's go ahead. So I've got my lecture examples for 4.1, and I also printed out my lecture example page for 4.2 because we're going to start 4.2 this morning. 4.2 goes over a couple days, and so we're going to do that. And I think there's only one homework assignment for 4.2. It's like it isn't like 1.1 where we split it up into two separate homework assignments. 4.2 has only one, but the lectures themselves will take place over a couple days. Okay, so so just as a excuse me, as a reminder, so this is chapter 4.1. This is stuff that we did on Monday. So when we were talking about 4.1, it's just like an intro chapter. You're going to see how we're going to pull in some of the concepts from 4.1 when we start talking about the rest of chapter 4. When we get into 4.2, you're going to see kind of like why we spent some time on this stuff. It's sort of a debate, like why are we belaboring this point on 4.1, because some of it doesn't really apply, but some of it does. And that's why I wanted to spend some time on 4.1. So just as a reminder, 4.1, we were talking about some vocabulary, right? So I have a polynomial, okay? And the polynomials, say, for example, we've been using one that goes up to like the 4th power, the 5th power, whatever. And when I talk about partial sums, I'm talking about taking only part of my polynomial. So a first order partial sum are all of the terms up to and including when x has a x of 1. Okay, so that would be like whatever my constant term and then my coefficient times x to the 1st power. My 3rd order partial sum is going to be all those terms up to and including when x has a power of 3. Now the thing to keep in mind is if I don't have a cubic power in my polynomial, you can pretend that your polynomial has a 0 times x cubic term. Okay, so in that case, like your 3rd order partial sum is going to be the same as the next lowest power that has something on there, has like an exponent. This is just a recap of the stuff that we talked about. All of these things, partial sums, these things are an approximation of the polynomial itself. Whenever we do an approximation, we have to talk about error, right? Because I'm just approximating. You can think about like whenever you round off a decimal, that's like approximating what your decimal is. You've got an error. We call that a round off error, right? So now when I've got my polynomial, okay, and I'm only representing it with a partial sum, the way that we think about our error is taking a look at what's left over. Like, what did I leave behind? What terms did I not use? Like if I did a 3rd order partial sum, but I have terms in my polynomial that go up to, say, the 5th degree, I've got like a 4th order and a 5th order term, and those become my remainder, okay? And that remainder, the absolute value, the magnitude of that remainder becomes our error, part of our error calculation. When we do the error calculations on our polynomials and like more of chapter 4, we're going to see the error, takes on this sort of we try to narrow down the error and make it very precise, but it's still like what we call an upper bound on the error. We want our error to be less than this value. Okay, we always want our error to be less than the value. If the error is more than the value, then maybe I need to rethink my approximation and do something different. Okay, so let me move on to example 3 on chapter 4.1. So this is the lecture examples for 4.1. This is what we started on Monday. And I'm moving on to lecture example number 3. So, and why do I want to think about this one? Because I'm trying to use these examples here because these are more simple, so that when we get into later parts of chapter 4, right, then we can, talk about like what was it that we're actually trying to pull together. Okay, so I've got this polynomial here, 7 plus 3 times x plus 2 minus 5 times x plus 2 to the 4th, okay? And so the first thing that we notice is like all of our x powers, all of our x terms are in the form of x plus 2. Okay, that's going to be a common thing that when we talk about approximation. And what this means is that the polynomial is centered at, we're going to go like this, x plus 2 equals 0. I'm going to subtract 2. So then x equals minus 2. So it's centered at x equals minus 2. Okay. And why are we doing that? What does that mean by centering? So when we say that our polynomial is centered, that means that our whole focus, how we're looking at the polynomial, is taking place around minus 2. So you can think about like I've got here's my x-axis, here's my y-axis, here's +1, here's 0, -1, -2. So my polynomial is doing something, right? I can plot this out and then take a look. It's a quartic, so it's probably, doing, something like this. So when I look at around -2, I'm going to be focusing my attention around -2. So like before we were saying we're going to focus around 0. And the reason we're focusing around 0 is, look at our polynomial, it was just plain old x, which means it's x like minus 0 raised to the 2nd power, x minus 0 raised to the 5th power. Okay, if you don't see x minus something or x plus something, that means that it's centered at 0. This is kind of part of our terminology that we're learning for our polynomials. So this is centered at x equals minus 2, right? That means I'm going to be taking a look right around my minus 2 area. So I'm just going to kind of circle this area here, right? I'm going to look at that. So now what we're doing is we're looking at values of x that are really close to -2. So when I say really close to -2, I'm going to go, like I'm really zooming in here, like this is really an exaggeration. So this is like -2, I'm going to go, this is, this value here is -2.1, this value here is -1.9, right? And I just want to be able to look at values within plus or minus 0.1 of the place where I'm focusing my attention. Okay, so that's what we're doing here. So that's like saying before, when x is getting really close to 0, now x is getting really close to -2, right? So this is where we're focusing our attention on. So when x gets really close to where we're focusing our attention, right, then what's happening? And the reason we're doing this is because we're going to narrow our focus so that our approximation, right, of our polynomial approximation of some function is focusing on just a very specific value. And why do I focus on that value? Well, maybe it has some relevance to a function I'm trying to solve. Okay, this is just an academic example, but in the real world, I want to know, there's some reason. I want to know what's happening at -2. It's important. So I'm going to, narrow my focus and come up with an approximation right at -2. So, okay, so what's the maximum error we can have by approximating our polynomial q of x by q1 of x. Now this doesn't mean first derivative, it means our first order partial sum. So let's write that down. So q1 of x is first order partial sum. Okay, first order partial sum means all those terms up to and including where x has a power of 1. So my first order partial sum, I'll write it like this. Right, I'm going to look here, this one, so we don't write like 1 as our exponent, but I'll put it in there. So that's 7, that's our constant term, 3x plus 2 raised to the 1st power. I'll put it here so you can see. So that this term and this term match each other. Okay, so this is our first order partial sum. Okay, so this is a polynomial centered at -2. We're going to look at values right? So we're going to look at values. Within, this is going to be -2 minus 0.1 and -2 plus 0.1. So I'm looking at values plus or minus 0.1 of -2. And we were told that 0.1 comes from here. Okay, so what we would do, how I would write this and how you're going to see this in later parts of chapter 4 is it's going to look like I'm going to go minus 0.1 is less than or equal to x plus 2 less than or equal to positive 0.1. Okay, this is where I'm focusing. It's like my central focus plus or minus 0.1. Okay, or it's also written like this: the absolute value of x plus 2 is less than or equal to 0.1. These two are equivalent statements. Okay, this is an absolute value. Okay, and we're going to use this methodology in later chapter sections to actually come up with values, how we're going to be determining things. So kind of like we're using the chapter 4.1 as an intro into sort of methods. Okay, so let's talk about the error. So the error in approximating. Okay, so we were told to look at a first order. That means I've got a first order error is what I'm looking at. Remember, our error is the remainder. We call it a first order remainder, but what that means is, right, I've got my polynomial, it's a fourth order polynomial, and my first order partial sum goes up to here. The first order remainder is everything that's left over after I take away that first order partial sum. Okay, so let's write this out. I'll write it all the way out. When you do this, you can just look and see what's left over, but we're going to write. So it's our whole polynomial minus our first order partial sum. So it looks like this. And it's a magnitude, right? I'm looking, that's why I put the absolute value there. So I'm going to go, so this is my polynomial 7 plus 3x plus 2 minus 5x plus 2 to the 4th. Oops, sorry, I don't want to do that. Minus 7, this is my first order. Where's my first order? Plus 3x plus 2 to the 1. And there, and my absolute value there. Let me do this. Get rid of this part here. Okay, so, right, so I'm taking my whole, this is my q of x, and this is my q, my first order partial sum, and I'm taking the magnitude. Okay, so what happens, right? 7 minus 7, 3x plus 2 minus 3x plus 2. So what I'm left with is absolute value of minus 5x plus 2 to the 4th, right? And so what can happen is I can go, okay, the absolute value is going to get rid of this negative sign. So this is going to be 5x plus 2 raised to the 4th. Right? This is how we write it. Now remember what we said, this absolute value of x plus 2 has to be less than 0.1. So I can plug in, right, let's do this. I'll put a little, oops, there, and then here. So I'm gonna replace, I'm gonna substitute 0.1 with that thing right there. So then this becomes 5 times 0.1 to the 4th. Be careful, you know, it isn't gonna be 0.1 plus 0.2. We're talking about, we wanna go, we're centering this at -2, and I'm going to go, you know, plus or minus, but really that window that, you know, plus or minus where I'm centering it at is at 0.1. So that's the important bit that we're thinking about. So I substitute in 0.1 for the absolute value of x plus 2, raise that to the 4th, multiply it by 5, and I'm going to get 0.0005. Okay, this right here, this is the upper bound, what we call the upper bound on the error. Okay, and this is what we get when approximating our polynomial with our first order. This is a first order polynomial, Q1. Okay. So remember, 4.1 is an intro, and we're starting to get into sort of the frame of mind and the reference point of how do we actually convert, how do we think about these, errors. What does it mean to, approximate a, a function with another function with a polynomial? And then when we approximate it, what's our error like? Okay, so that's this part right here. So the next example is actually a conversion process where we're given a polynomial that's centered at x equals 0, but now I want it to be focused at a different value. So the reason that we're going to change and we're going to convert our polynomial from being focused at 0 to being focused at that different value. And the reason we do that is because if the polynomial, like this one, is centered at x equals -2, but if I want to look at values other than x equals -2, then my approximation is not going to be so good. My error is going to go way up. Okay, because this right here, we're centered there at x equals, we're centered here at x equals -2, right? That means that my approximation is going to be pretty good at x equals -2, because we're going to find out in chapter 4.2, we're going to start doing that today, that the whole process of making this approximation is based on where I'm centering it, okay? But if I center it at this value, but then I want to look somewhere else, my approximation isn't so great. As we go along in chapter 4, we'll actually graph these things out and we'll be able to see it. So my approximation is not so great farther out. So I need to have a process of shifting, converting a polynomial that's centered at one value to a polynomial that's centered at another. Okay, I sometimes hesitate to do this example because it seems really long and belabored, but I just want to say first off that you won't have to convert a polynomial from one center point to another. But the reason I'm going through this example is because the process of doing this is really similar to how we're going to do our polynomial approximations of a complex function. And so I want to give you that skill set of how do we actually make this, okay, because we're going to be needing to do this in chapter 4.2. So that's why we're going to do this. But just know that if you're given a polynomial here, you won't be asked to reconvert it to somewhere else. I think, I don't know if you have a homework problem like it, but like on a test or quiz, we won't ask you to convert it, to move it somewhere else. But the process is important because we're going to use this process elsewhere. All right, so we've got this polynomial. You can see 4 minus 2x plus 5x squared plus 9x to the fifth. Now this thing is centered at x equals 0. How can I tell? Because my x is just plain old x. It's like x minus 0 raised to the first power is the same thing as x raised to the first power. Whereas the previous example was x plus 2 raised to the first power. So that whole like little binomial, that binomial term there, that whole thing, right, was basically where my x was being centered. So we want to look at behavior close of x close to 1, which means I want to refocus, I want to recenter this so that this is going to be at x equals 1. So if x is equal to 1, if I subtract 1, I'm going to get x minus 1 as my terminology. Okay, so instead of x minus 0, I'm going to have x minus 1. Look, I say x equals 1. I subtract 1 from both sides. I'm going to get x minus 1 as my term here. Okay, so this is what we're going to be working with. But I can't just plug in x minus 1 and have it be the same polynomial because the coefficients are all going to be different. Okay, so how am I going to figure out what my coefficients are? That's the process. Okay, the coefficients are actually really important. Okay, so let's do this. So our goal, let's write down our goal. Our goal is to have a polynomial. And I'm going to write it like this: b sub 0, these are my coefficients. So b sub 0 plus b sub 1 times x minus 1 to the first power, plus b sub 2, x minus 1 to the second power, plus b sub, whoops, that's a 3, x minus 1 to the third power, plus b sub 4, x minus 1 to the fourth power, plus b sub 5, x minus 1 to the fifth power. How do I know when to stop? I'm stopping because I've got a fifth power and a fifth power. Okay. So that's how I know. So I've got to come up with, I need to derive b sub 0, b sub 1, b sub 2, 4, and 5. I need to derive these values, these coefficient values, okay? And they're going to be related to the values that are there, and they're certainly going to be related to the polynomial that we're working with, but I have to come up with them. They're going to be unique to this x minus 1 representation of my polynomial. Okay, so let's take it by steps. So the first step that we need to do is, I'm going to plug in x equals 1 into p of x. Okay, if I plug in x equals 1, I'm going to go p of 1 equals 4. So this is going to look like, actually, let me write it out first as, this is going to be b sub 0 plus b sub 1, right? I'm plugging it in here first. This is going to be x minus, sorry, 1 minus 1. 1 minus 1 to the first power plus b sub 2. This is 1 minus 1 to the second power, and so on and so forth. Okay, so the only one that doesn't cancel out is my b sub 0. And that's equal to this polynomial here. That's equal to this polynomial with 1 plugged into x. 2 times 1 plus 5 times 1 squared plus 9 times 1 to the 5th. Okay, so I'm going to multiply it. So this is going to become b sub 0 because all the other terms cancel out, right? Let's do that. So this becomes 0, this becomes 0. So all these terms cancel out, and all I'm left with is b sub 0 on this side. And then these are all numbers, right? This is 4 minus 2 plus 5 plus 9, right? Because 1 squared, 1 to the 5th, that's all just 1. So I add all that up. So I'm going to get b sub 0 equals 16. So that gives me my very first piece in my recentered polynomial. Okay, my next step is I'm going to differentiate, take the derivative, differentiate each side. Okay, so it's going to look like this. P prime, this is first derivative. This is a prime mark, not a number 1. So P prime equals. So I'm going to take the derivative right here. So when I take the derivative of a constant term, that becomes 0. So the derivative of the constant term becomes 0. Then what I have left is, 1 times b sub 1, right? And then I take the derivative of what's inside, okay, for my chain rule. So I get b sub 1 plus 2, b sub 2, x minus 1, plus 3, b sub 3, x minus 1 squared, plus 4, b sub 4, x minus 1 cubed, plus 5, b sub 5, x minus 1 to the 4th, right? I just took the derivative of all of that. And that's equal to, I'm going to take the derivative now of this, right? Oops, sorry, you can't see what I'm doing. I'm taking the derivative of my original function. So the 4 drops out, and I'm left with minus 2 plus 10x plus 45x to the 4th. And we're going to go through the same process right here. Okay, so my step 3, plug in x equals 1 into both sides. Okay, so into here, plug in x equals 1 into both sides, and then we're going to get a value. So it's going to be p prime of 1 equals, right, what's going to be left over? This is going to be b sub 1 plus 2 b sub 2 times 0 plus so on and so forth. These are all zeros, equals minus 2 plus 10 times 1 plus 45 times 1 to the 4th. Okay, right, so I plug in 1, because 1 is where I'm centering it. Yeah, it's okay if your Wi-Fi keeps logging you in and out, just keep coming back, and then I'll just keep admitting you into the class, and then I'll post a video later today, so in case you missed something, then you can see what's going on. Okay, so let's plug it all in. So what do we get? Right, so this all stuff, I'm going to get b sub 1 equals minus 2 plus 10 plus 45, and I'm going to get minus 2 equals 53. So b1 equals 53. So we're going to keep iterating this. We're going to keep going through until basically we're working our way down. So I don't have any more b. I'm going to work on b sub 2, then b sub 3, b sub 4, b sub 5. So I'm going to just do that. I'll do a couple more out. So I'm going to differentiate. And plug in x equals 1. So I'll lump it into one step now. So this is going to be my second derivative. Oops. That x is going to look like 2b2. This is, I'm doing this out 3 times 2, right? So I'm taking this derivative. So 3 times 2 times b3 times x minus 1. I know it's 6, but I'm trying to show you intentionally what this means. So there's a b, x minus 1. Sorry, I'm running out of space here, cubed. Okay, and now we're going to plug it in. So if I plug in x equals 1, 1, I'm going to get, so this is going to look like 2b2. Everything else is going to become zeros equals, oh, and then my other side. So if I take the derivative of this right here, right, this is going to be 10 plus 45 times 4 times x cubed. Okay, so this is going to be 10 plus 45 times 4 times 1 cubed. And I'm going to divide by 2, so then my b2 is going to equal to 95. Okay, so I'm going to keep iterating on that. Okay, and then I'll put out what it looks like, and I'll put up what the values are. Okay, so I'm just going to roll right through. Give you guys a second to finish writing that, and then I'm going to turn the page. Don't worry, I'll scan in the 4.1 later. Right. So we're going to keep iterating until all the b sub k are solved for. Okay, so that means we just went up to b sub 2, so I need to do b sub 3, b sub 4, b sub 5. Okay, so what's going to happen is this. So my step 5, taking the third derivative, I'm going to go through more quickly just so I can see. I'm going to actually start to summarize, right? So the reason that I multiplied all these numbers out, right? 3 times 2, 4 times 3 times 2, 5 times 4 times 3, and I think there should be, we'll find out that there's a 2 in there when we take the derivative here. This should start to look familiar. This is a factorial, right? So this is 3 factorial. So 3 factorial is 3 times 2 times 1. Okay, so this is 3 factorial. So all I did was I said all of this stuff, right, goes away. And then I will actually make this at x equals 1. Because that's how I get all that stuff. So all this stuff goes away. So my third coefficient is my third derivative evaluated at that point, divided by this number here, 3 factorial. Okay, so this is important because this becomes part of our formula for how we're thinking about coming up with these coefficient values. This is something that we're going to use in 4.2, 4.3, so on and so forth to help us come up with our coefficients. Okay, so let's go ahead and we're actually going to do it out. So this is okay, so I solved for b sub 3. So I'm going to go through more quickly. So my fourth derivative. Okay, so you can see how this is 5 factorial. This is 4 factorial, right? So I'm going to summarize this here too. I'm going to say b sub 4 equals my fourth derivative divided by 4 factorial. Start using the factorial notation. Okay, that's our summary. Now I'm going to plug things in. So this is my fourth. So this is going to be this comes from my polynomial itself. Remember, these are all just to come up with the coefficients, okay? Because we're reshaping our polynomial. I'm going to do my fifth. This is my last one because I have a fifth order, so I have five derivatives I need to do. This is my fifth derivative. Okay, actually, all right, so I found my B5. All right, so what I'm gonna do is I'm gonna summarize what our different coefficients are, okay? I'm gonna put it all in a list so that you can see the formula for the coefficients, because we're gonna need that in 4.2. Don't worry, if it isn't quite making sense, you can write it down, roll with it, okay? Because we're gonna do a lot of practice with these and we're gonna build on this concept, okay? But like I said, shifting a polynomial to another spot isn't something that we're actually gonna be doing, but this process here of coming up with the coefficients is something that we're gonna do in later parts of chapter 4. It's actually really important for us to be able to figure out what is our polynomial approximation. Okay, so let me just summarize these coefficients. Okay, so this looks like B sub 0. This is all evaluated at 1, okay, at x equals 1. Okay, B sub 1, my first derivative, oops, B sub 2. This is a generalized format of it. Okay. So let's recap, right, from what our original was. Right, so our original polynomial was at where a was equal to 0. X was focused at a, centered at a. So remember, we would started off with p of x equals 4 minus 2x plus 5x squared plus 9x to the 5th. Okay, and now with our new coefficients, we have all these new coefficients that we just derived based on our polynomial, based on like our derivatives. Okay, so this is, we're going to use this when values of x that we're looking at are close to 0. Okay, when I'm looking at values of x that are, you know, plus or minus some small number around 0. If I want to shift my focus to be x equals 1, so this is the polynomial centered at x equals 1. This is the whole derivation that we just did, right? This one's going to look like, so my new polynomial is going to be my first constant term, my first coefficient, my second one, 53, x minus 1. This is to the first power. You don't have to write to the 1, but I'm putting it there so you can see it, plus 95, x minus 1 squared, plus 90, x minus 1 cubed, plus 45, x minus 1 to the 4th, plus 9, x minus 1 to the 5th. Did I do that? Is that right? The 5th one? Okay. So this is the polynomial that we would use when we're looking at values of x that are close to 1. Close to 1. Okay. So don't worry about if like shifting a polynomial seems kind of confusing, like why did we do that? What was going on? Okay, the important bit is this whole process here. Okay, how did we actually come up with the coefficients? And the fact that when I have a polynomial, if I want to look at values close to a specific value, x equals 0, x equals 1, x equals minus 2, whatever, I need to make sure that my polynomial is centered at that value. Okay, because then my approximation is going to be much, much better at that center point than it is elsewhere. Okay. All right. It's a lot to take in. Don't sweat it. Like I said, if it's not quite clicking, okay, we're gonna go over a lot of examples as we go. This is just like kind of to get your mind wrapped around the idea, okay? And now chapter 4.2 is when we're actually gonna jump in and do stuff, okay? So let me start talking about 4.2. I'll save about 5 or 6 minutes or so. We can answer questions at the end. And plus also, don't forget I have office hours today if you guys wanna come by and ask questions about that. Okay, I'll scan this in later so you guys can have this as part of your notes. So take a look at the Canvas page for that later. Okay, and I'm also going to scan in, I forgot to tell you, I'll scan in the solutions for the quiz. I haven't scanned in the quiz solutions yet. You guys should have been able to see your quizzes and your, like the rubric. If you look at the Canvas page where your quizzes are uploaded, I've written comments, sometimes off to the side, sometimes on the page itself, so you guys can take a look to see like where points were taken off and where you went wrong and your thought process on some of the stuff. I'm going to scan in the solutions later today for the quiz so that you guys can compare it with your answers and see how things went. Okay. So chapter 4.2. So remember, 4.1 was we're approximating a polynomial with another polynomial, or with only part of itself, okay? But 4.2 is we're going to approximate a non-polynomial function with a polynomial. So this thing is called approximation of functions. Okay, and I'm going to write, let's do a little subtitle. So the functions are non-polynomials. They're complex functions, exponentials, trig functions, logarithmic functions, rational functions, things that I can't easily integrate. I need another set of tools to reduce them down to a polynomial so I can do stuff with them, okay? Functions are non-polynomials, and then we're going to approximate these non-polynomial functions with a polynomial. And why do we do that? Because polynomials are much easier to work with, right? I can take a derivative easily, I can integrate easily, I can do all sorts of stuff easily. It's an approximation though, so like things, I'm gonna lose some, precision on it. So I have to always think about the error when I'm doing an approximation, but polynomials are much easier to work with. That's why we bother. Also, like your calculator, will do this, conversion process into a polynomial, and then it will do things to it. If you look at, I think a lot of you like to look at those online solution solvers. You have to be very careful, those like Wolfram Alpha or other solution solvers, because what they do actually is convert it to a polynomial approximation, and then they do stuff. So I can always tell if you guys are using those things because they all follow a similar plan of how they're processing stuff. So polynomials are easier to work with. The thing we need to think about is where is our focus centered? Like at what x value? X equals a is what we're going to be thinking about. So it's centered at x equals a. X could be equal to 0, x equals 1, x equals whatever. Where are we centering this perspective? Okay, so let's talk about some requirements for approximating a function with a polynomial, okay? So some things that we want to be true, and we're going to use these requirements to actually derive the polynomial. Remember, we are the ones who are coming up with the polynomial, and the polynomial itself is going to be based on the function, okay? So these are the requirements that we wanted to have, but given these requirements, we're going to derive this polynomial with these requirements in mind. Okay, so this isn't some polynomial we're going to be guessing at. We're going to make this polynomial ourselves from the function. Okay, so the first thing is at x equals a, our function that we're trying to approximate and our polynomial, they have the same value. At a, oops. At a. So we would say f of a equals p of a. Okay, and that's a given. It's like I've got this really complex function, it's doing something, I'm going to approximate it with a polynomial at that x equals a where I'm looking. That x equals a and that function have the same value. They intersect at that point, okay? Similarly, right, number 1 and number 2 are like two sides of the same coin. Similarly, our function and our polynomial have the same 0th derivative. The 0th derivative is the function, right? So that's why these are like the same idea at x equals a, okay? So what that also means is that the graphs of p of x and f of x intersect at, whoops, can't see that, at x equals a. So the point a, f of x equals a, oops, sorry, this is a, f of a, p of a. It's an a. Okay, so the graphs intersect each other at that point, x equals a. But these are functionally the same idea. Okay. So I can say, watch this, my function and my polynomial have the same rate of change at the same rate at the point x equals a. What does it mean to have the rate of change? We're talking first derivative here. Okay, so what this means, i.e., the function and the polynomial are close in value near a. So not only are they equal to each other right at a, but as we get closer to a, the function and the polynomial are changing at the same rate. So they're really close together. They may not be exactly equal like they are at a, but they're really close together. Since the graphs have the same tangent lines at x equals a. So that means that our first derivative at a is equal to the first derivative at a of my polynomial. Remember when we did, when we came up in that 4.1, we did that whole creation of the coefficients. We used the derivatives evaluated at that center point where we're centering the polynomial. It's the same idea right here. We're going to use that same notion, which is why I went through that long process. Okay. So not only are they changing at the same rates, the first derivatives are the same. The second derivatives are the same at that point A, which means that the graphs have the same concavity at x equals a. Okay, and so on and so forth, right? So this function that we're talking about, f of x, this function has, we're going to say it has like n derivatives, but n could be infinite, right? E of x has an infinite number of derivatives. My sine of x has an infinite number of derivatives. We're talking about functions that are complex enough that they have an infinite number of derivatives, essentially, okay? So this whole process where I said the 0th derivative, the first derivative, the second derivative, it's going to be true all the way down, okay? The third derivative, fourth derivative, whatever, at a, my function and my polynomial derivatives are going to be the same, okay? I'm going to turn the page. So at x equals a, we want the graphs of our function and our polynomial to be as near as possible and as similar in behavior as possible. Okay. And the reason we do that is because I'm trying to come up with an approximation. I want them to be as similar as possible within some boundary of A. How do we define that boundary? That's a whole process of discussion that we're going to talk about in the rest of chapter 4. How do we make this good? How do we judge how good this approximation is? That's what we're going to be doing in chapter 4. So what we're going to do is we're also going to assume that our function is what we call n times differentiable. I can take n derivatives. you know, if I have a polynomial of fifth order, right, after 5 derivatives, my derivatives turn to 0, right, because it's all just constant terms after that. But if I've got e to the x or e to the 2x, or, you know, e to the x times sine of x, these things have an infinite number of derivatives, okay? So we say n times differentiable, but n could be infinite, okay? And these are n times differentiable at x equals a. We'll narrow our focus just to that point right there. So our goal is to get a polynomial in this form. So I'm going to say my polynomial p of x equals my sum. Remember, polynomial is just the sum of terms, right? I'm going to start at 0, and I'm going to go up to n. We're going to start off with n, but really n goes to infinity, right? I'm going to say I've got this coefficient, I'll call it c, x minus a to the k. And let me define c sub k is equal to my kth derivative evaluated at a divided by k factorial. Okay, this is the kth derivative. This is the same thing right here. And then I'll say f sub k of a is kth derivative evaluated at x equals a. Okay, so that's how you want to be reading this in your mind. Okay. There's a lot to take in, especially chapter 4.2, when we first start this whole concept. But don't worry, as we go, we're going to do a lot of examples. Okay, you guys will have the lecture examples posted online, so you guys can take a look at the solutions for them. And that'll help you kind of summarize like what it is we're trying to do. Okay. So generically speaking, this is what we're trying to do. These are our requirements. So let's talk about, there are two different types of polynomials. They're actually related to each other. The first one that we're going to focus on is called the Taylor polynomial. Named after a mathematician whose last name was Taylor. So Taylor polynomial of our function, f of x, which is centered at x equals a. Okay, so remember, Taylor polynomial is a process of creating an approximation of some complex function with a polynomial. And we're focusing our attention at the specific value a. So let's assume f of x is a function n times differentiable. We don't want this to go to 0 without differentiable at x equals a. So just like that requirement that we just talked about. And I write the Taylor polynomial notation. It looks like this. Capital T for Taylor, F for functions, my subscript, N tells us the order, X, this is my variable, and then A, which is where I'm centering it. Okay, this is our notation for a Taylor polynomial as a function of X centered at A. Okay, and it could be first order, second order, 10th order, whatever, it's a function. And it's going to look like this. I'm going to sum, I'm going to start at 0, and I'm going to go up to n. I'm going to write out my coefficients here. So here, okay, this is my coefficient. That's what we just did up above, times x minus a to the k. This is a polynomial, okay? So in no way, shape, or form should I have anything other than numbers and like some kind of polynomial, x minus a to the k power, okay? The functions that we're going to be working with are like e to the x, sine of x, cosine, whatever, okay? In no way am I going to have sines, e's, or whatever in here, except as numbers, okay? So let's write this out. I always like to write this out as a polynomial. So this looks like this. When k equals 0, this is going to be my 0th derivative is just my function evaluated at a. Oops. My function evaluated at a plus my first derivative evaluated at a. This is divided by 1 factorial, which is just 1. So I'm going to drop it, x minus a. Okay, there's a 1 power here. Plus my second derivative evaluated at a divided by 2 factorial. Okay, I'm writing 2 factorial, even though 2 factorial is equal to 2. I'm writing 2 factorial, x minus a squared. Plus, you can see where this is going. Third derivative evaluated at a divided by 3 factorial, x minus a cubed. Plus, we're going to go so on and so forth, all the way up to however many we say. My nth derivative evaluated at a divided by n factorial. times x minus a to the n, right? You see these are all related. Okay, these are all the individual terms of the polynomial. See how we start off at our lowest term and we work our way up in degree terms. Okay, and if I'm only going to represent, like my ultimately n's going to go to infinity, but I'm not going to sit here all day and write out all the way up to infinity. I'm just going to maybe go up to like the first handful of terms, and I'm going to say this is a third order Taylor polynomial. It's a partial sum because the Taylor polynomial is going to go on forever, or it's going to go on for a really large number. Okay, so nth order details out my highest degree term. It will often specify, do the third order Taylor, or we'll say do the first several terms and then tell us what order it is, that kind of thing. So I'll let you finish writing that, and then we'll talk about a subset of the Taylor polynomial when when a is equal to 0. So this is your Taylor polynomial, and this is writing it out. Okay, when I do these problems, when I do example problems, when I do the homework problems, I write this, I write out a whole, the first sample of terms, and it helps me keep track of what do I actually need to do? What's my process that I need to do? Okay, so let's talk about a subset of the Taylor, and you'll see this in your book. This is called the Maclaurin Polynomial. I think Maclaurin was like a protege of Taylor or something, but he basically said this is when a equals 0. So we're focusing at 0, and we have a subset. We do its own, it gets its own polynomial because often we want to look at what's happening around 0. 0 is important, right? And enough to get its own name. So this is Maclaurin polynomial of our function of x, and this is when a equals 0. So we would write it like this, right? It's a Taylor, we still write Taylor, and we would say it's nth order, it's a function of x, right? It's focused at 0, but technically speaking, because there's a 0 there, we actually write it like that. So this is our notation for Maclaurin polynomial at a equals 0. So its nth order, let's write out what it looks like as a polynomial. So I would say, right, as a summation, k equals 0 to n, right? Same idea, same exact process, except instead of some a value, I'm doing it at 0. Right, you notice how I don't have to write x minus 0 to the k power, because it's the same thing as x to the k. And what this looks like is my function itself evaluated at 0, first derivative evaluated at 0 times x plus second derivative evaluated at 0 all over 2 factorial x squared plus third derivative evaluated at 0 all over 3 factorial x cubed. See how this is going to be a coefficient of x squared or of x cubed, plus so on and so forth. My nth derivative evaluated at 0 all over n factorial x to the n. That's Maclaurin. A is equal to 0. Same process. Everything is identical. Instead of a being equal to pi over 2 or a equal to 1, a is equal to 0. Okay. Okay, so just a note before we jump into examples, a note to keep into mind. For n big enough, when we say big enough, we're actually going to talk about what that means. How do we know what's big enough? And that's going to be a whole discussion of error. Where do I want to keep my error range in? So for n big enough, my Taylor, right, my Taylor polynomial approximates our function well when my value of x is close to a. We're going to see that. We're going to do examples. We're going to do we're going to derive a Taylor polynomial at x equals some a value. We're going to evaluate it at x values close to that a value. We're going to see what it looks like. And then we're going to say, well, let's evaluate it at x values, farther away from that a value. And we'll see that the approximation isn't so great. Okay, it's not horrible. Okay, but the farther away you go from a, the worse the approximation gets, which was that whole discussion of why we're centering our focus at that a value, because I want the approximation to be good. Okay. All right. So let's go ahead and we'll think about example number 1. Okay, we're going to actually dive right in. So this is chapter 4.2 and part 1. I broke up the lecture examples into part 1 and part 2 because we usually spread this out over a couple of days. So you'll see that on our notes. So part 1. But like I said, I think the homework is just all one piece. So we've got the function e to the x, f of x equals e to the x. We're going to find, right, our nth order polynomial, Taylor polynomial of x centered at 0, which means we're doing a Maclaurin. We want to use the first and third order. So this is n equals 1 and n equals 3. Maclaurin polynomial. Maclaurin means a equals 0 to approximate, right, when x is equal to 0.1. So I'm looking, I'm centering it at 0 because I want to look at values of x that are close to 0.1, that are close to 0. All right, so I have to set up, I like to set up a table. So I have my derivatives, right? And I'm going to evaluate this at x equals a, which is equal to 0. Okay, so my 0th derivative is just my function always. So my 0th derivative, it's a 0, evaluated at a, right, is x to the, e to the 0. Everywhere I see an x, I plug in a 0. E to the 0 is equal to 1. This you know, the derivatives, all the coefficients are going to be 1, because my first derivative of this function here is equal to e to the x, which means my first derivative, e to the 0, is equal to 1. My second derivative is the same thing. It isn't always going to be so straightforward. E to the 0 is equal to 1. Okay, so we're going to need, it said first, n equals 1. We're going to need this for n equals 1, and we're going to need this for n equals 3. Okay, I just went down the line just so I could, I like to prefetch all this stuff so that we can then just plug things in and evaluate it. All right, so let's write it out. So first order, it's going to look like this. So I've got my, I'm going to start filling in the blanks. Right, so my first order Taylor polynomial evaluated at x, evaluated a equals 0, which is my Maclaurin, first order Maclaurin. Let's write it out. So I've got my oops, this is a 0, x, it's a 0. Okay, so these are the values that I'm going to plug in. So it's going to look like, I go up here, I go f sub 0 evaluated at 0, that's equal to 1, plus my first derivative evaluated at 0, that's equal to 1 times x. Okay, so this is my first order Maclaurin polynomial is simply 1 plus x. And that represents the function f of x equals e to the x. Okay, so this is our first order Maclaurin polynomial for f of x equals e to the x. First order, because the highest degree term is 1. See, this 1 here matches that right there. Okay. They said to use the third order. So we're going to do that. So I'm going to say, I'm going to write out what my terms look like first in terms of like f of 0, you know, so on and so forth. And then I'm going to plug them in. This is going to be f of 0 plus f of 1 of 0 x plus f, my second derivative divided by 2 factorial x squared. And we're going up third order, so it's going to be plus okay, so these are the values that I'm going to plug in. These are the coefficients that I figured out before, right? X cubed, x squared, x to the 1, all those things make up the part of my polynomial. Okay, so let's plug in. So this is going to look like, so this is 1 plus, right? I look back up to here. What did I get for my values? So this is 1 times x plus, this is 1 divided by 2 factorial x squared. This is 1 divided by 3 factorial x cubed. Okay, now I'm going to multiply this out, so I'm going to get my third order Maclaurin polynomial is going to be 1 plus x. 2 factorial is equal to 2. This is 3 factorial, that's 3 times 2 times 1. So this becomes, and that's it. So here, this is our third order Maclaurin polynomial for f of x equals e to the x. And we were told, do the first order, third order, whatever. You're going to be told what order to be working with. Okay. In general, let me just write out the general form, the nth order. So it looks like this. So I would say TFN x looks like this. So it's going to go as a summation form. You sometimes, practice writing it as summation form, kind of trying to generalize this, because you'll have to do this stuff as you go. So this is going to look like, right? So if I fill this in, it's going to be 1 plus x squared all over 2 factorial plus x cubed all over 3 factorial plus x to the 4th all over 4 factorial plus so on and so forth, x to the n all over n factorial. E to the n, e to the x, I'm sorry, comes up a lot, so kind of make sure that's in the back of your mind. Okay, so this is our general. Now we were asked to take a look at when x is close to 0, when x is equal to 0.1, what do we get as an approximation? If you guys, I'll give you a minute to finish writing that, and then I'll turn the page. All right. Remember, I'm going to post this stuff later too, so you can see it. All right. So the question is, how well does our Maclaurin it's a 3. Say approximate. How well does our first order and third order approximate e to the 0.1? Now I can just plug in e to the 0.1 on my calculator. We start off with functions that are straightforward. I can plug them into my calculator and look. Okay, just so you guys can have a reality check on stuff. So calculator e to the 0.1, I plug this in, I'm going to get 1.105170918. So like I said, we're starting off with things that are easily done in our calculator so we can learn the process. But the ultimate goal of this is to do this for functions that we can't plug into our calculator. So we learn it on things that we can cross-check, and then we apply it to things that we don't know. All right, so let's take a look. 0.1. It's going to look like this. Now, everywhere I see an x in my approximation, remember this was 1 plus 1 times x. Okay, so my first order Maclaurin polynomial just gave me this bit. So I've got a pretty sizable chunk of numbers that I'm leaving behind. That's kind of expected. So let's try our third order. Everywhere I see an x, right? So this was 1 plus x squared all over 2 plus x cubed all over 6, right? So I'm going to put this in 1 plus 0.1 plus 0.1 squared all over 2 plus 0.1 cubed all over 6. Right, this is the polynomial. In no way, shape, or form should this have like e value, e to the x values, or like when we do sine functions. It won't have any sine functions either. Okay, so when I plug this in, I'm going to get 1.1051666. Okay, so 1.10551, and then it kind of breaks off right down here. So we get up to about 1, 2, 3, 4 places after the decimal, and then it flips off. So it's not too bad, right? I mean, it's in terms of, sort of back of the envelope, we're coming up with a pretty good estimate. I probably wouldn't want to like launch a rocket with that kind of an error margin. That's kind of like a, not too far out in terms of an error. But, I think in terms of just kind of trying to come up with a back of the envelope estimate, it's not so bad. Okay. All right, I'm gonna leave the next example for next time because it's a sine function and there are things I want to talk about. So we'll do this one next time. Make sure you guys, I want to stress this too, all the angles in this class are measured in radians. I saw in the quiz some of the angle measures were in degrees. I didn't take off points for it, but you will start to lose points and your answers will be wrong because we're going to start assuming that everything's in radians. So make sure when you do your homework, everything's in radians. Also, you probably want to write things in terms of pi. So if you're doing things on your calculator, trying to come up with angle measures, make sure you recognize that as pi over 4 or pi over 2 or what are those things, okay? So don't give me, this is going to be like roughly 1.5 something, something, something. So if you've got that on your calculator, try to figure out that that's actually pi over 2. All right, so we'll come back to this tomorrow, okay, 4.2, and then we'll pick up 4.2 part 2 also tomorrow. Okay, I think we've got like 2 minutes, not too much time, but does anybody have a quick question that they want to ask about homework specifically? Maybe we can look at if you guys like need an answer for like 4.1.
In the like 11 and 15 section, it says to rewrite the polynomial centered at a given a. Is that just the same thing as this?
Right, exactly. That's like exactly what we did in class today. So yeah, you can try, so 11 and 15, you'll want to recenter it. So that's exactly the whole process that we did today. And that's to help you kind of practice that whole thing. Yeah. So the stuff that you might see on the quiz are things that are close, that probably go up to maybe, question number 9, say for example. Okay, but those are the kind of questions that you would see. Is there a less tedious way to do Riemann sums at values like n equals 10? No, I'm sorry. Especially when it asks for all 3 methods. I'm telling you, you're talking about homework for chapter 2.6. I thought it was really tedious too. It just, chapter 2.6 homework is painful because it takes so long to do because it's not hard, but yeah, n equals 10, like why did they give me that? On like exams and stuff, typically you won't see, Riemann sums that are that high because we know you have a limited amount of time. But yeah, on the homework, you just kind of have to do it. I think that when we first did Riemann sums in calculus, we talked about them as a generalized summation form. So you could probably write a computer program to do it, but right now you got to do it by hand. So give yourself time to do it because it can be a pain because it's tedious. Okay, guys, I'll see you tomorrow. Have a great day. Rest of your day.
Thank you.
Take care.
Thank you.
Thank you.
Take care, guys.
Thank you.
Bye, guys.